Hello, I'm Alexander Jokov from modelizeIT, and in this video I'll be digging deep into the technical features and capabilities of the modelizeIT software. We'll begin by going over the unique capabilities of modelizeIT, including application identification, affinity grouping, wave planning, and reports for migration and modernization like capacity planning and license management. This is an example business application architecture diagram, auto-generated by the modelizeIT system from collected data. You can see a specific F5 load balancer pool that forwards requests to a couple of Apache Tomcat servers with specific deployed Java modules. You can see Apache requests forwarded via another set of F5 load balancing pools to a MySQL cluster. To understand the depth of modelizeIT's modeling, consider this. To deeply analyze F5 load balancers, modelizeIT understands F5 configurations and their programmatic rules that define how the requests are forwarded. In fact, modelizeIT can model thousands of middleware and software components out of the box. modelizeIT is a proven technology that is trusted by partners, enterprises, and governmental organizations. This includes 19 clients from the Fortune 100 list. Since 2012, our system has been used to collect data from over 700,000 servers around the world. modelizeIT offers by far the largest set of application models for the analysis of software configurations and application architecture. This includes thousands of software product models, ranging from IT to industry-specific applications like banking, manufacturing, gaming, and more. So, why do you need to understand application architecture? What you see on screen now is a representation of the typical data center sprawl and the dependencies that link business service components across hundreds, or in some cases thousands or tens of thousands of servers. We like to call this the giant hairball. Generating a snapshot of these server-to-server dependencies, or server process-to-server process dependencies, is relatively easy, and most discovery tools can do this without too much difficulty. However, this is not enough to plan a migration. Clients migrate business applications such as payroll, email, and expense reimbursement, not servers. So, to plan a migration, one first needs to identify and understand the architecture of all involved business applications. Once you start working on understanding client applications and begin planning their detailed migrations, you quickly realize that you're relying on client IT staff knowledge and availability. This creates a bottleneck. Progress depends on scheduling interviews, finding the right subject matter experts, and validating information that is often incomplete or outdated. As a result, early momentum often slows into a long discovery process before migration teams can confidently finalize application waves and dependencies. Typically, migration planning teams start working from well-documented and well-known applications, depicted green here, and make some quick initial progress. After that, client interviews can help with the undocumented portion of the information depicted yellow. Finally, there are business applications that are forgotten by client IT staff members, or for which IT staff members' knowledge is incomplete or incorrect. The red portion may be small, or as great as 50%. In any case, unless all business applications are addressed, a client data center cannot be vacated. Our goal at modelizeIT is to help accelerate the yellow portion and uncover the red portion of the application-related information. The modelizeIT migration planning pipeline consists of 3 stages. The first stage is mapping servers to business applications. After that, we group these applications into affinity groups. An affinity group is essentially a group of applications with critical dependencies that cannot be broken. Breaking these dependencies will result in a loss of functionality or downtime. Therefore, we consider affinity groups as the atomic migration unit. Finally, the last stage involves planning the actual migration waves. Each wave contains a set of affinities. The modelizeIT software can find the optimal plan of attack and package affinities together in a way that meets both technical and business requirements. We begin the application mapping stage by importing the business applications that are already known from the client. This can be from a CMDB or even just from a handwritten CSV file, or flexible. This gives the team a solid starting point. From there, modelizeIT uses its knowledge of thousands of applications and their internal characteristics to help identify and map the remaining servers much faster. Instead of relying only on manual discovery and tribal knowledge, this lets teams expand application coverage more quickly and with greater confidence. We want to emphasize that without modelizeIT, the application identification phase can be extremely difficult. Many clients have come to us with migration projects that have been stalled in the stage for years. On the other hand, with modelizeIT, together with insights drawn from our extensive studies on migration acceleration factors, we've been able to reduce the timeline for some large-scale migration projects from years to months. modelizeIT's application models are specifically built for migration planning analysis. The system understands the semantics of dependencies and IT components, rather than reducing the environment to server-to-server communication or raw traffic patterns. For example, the left diagram here colors 2 servers and all their software components violet, as well as coloring their dependencies. The right view here shows the same two servers, but now only the components and dependencies that define the architecture of this application are shown. Switching between these views using our software takes just one click. It's able to apply intelligent decision making to involve dependencies and software components like these. We'll now present a demo on how to identify applications using modelizeIT.
In this video, I will be going over the steps used for mapping unknown applications in corporate data centers. If we look at the capacity plan object, we can see that there is information on more than 600 servers. On top of that, we can see that the client has provided information on 25 business applications. In this setting, we don't know anything about any of the other applications. We only have information about the servers. The following will show the steps for mapping each server to business application. We will click on Unknown Applications, which as we can see is empty. If I click on Identify, we will be able to see the unknown applications in this environment. The system splits all of the servers into logical groups, which are servers working together performing some business functions. If we take a look at this application, Unknown Application 137, we can see that there should be two objects shown inside of it. The modelizeIT system decided that these two servers, one Windows and one Linux, are working together. These two likely form a business application or a group of connected business applications. We will be able to see what is happening here by creating a diagram. First, we will start with viewing the default architecture diagram. At this point, we only want to see the objects and dependencies that correspond to the business logic implemented on these two servers. The information displayed here, which we knew in advance, was that the client provided a list of subnetworks depicted by the usernet object. This is also available for us to view in the business applications object from the homepage. From the usernet, we can see that the users create connections to this Oracle WebLogic server, which is deployed on the Windows host. We can also see that this application is using an Oracle database on this Linux host. Now we will view the architecture with NAS diagram, which will include network storage. It shows that the servers have network shares and that users access information by using the file shares. There are also backup NFS shares on the Linux host. This host on the right, named TPAF-SAN02, is shown with the dotted lines because the client has not collected the data. The system is not populated with the information from this server. Still, we can see that it exists even though we do not have the data. The next diagram that we will look at will be the virtualization diagram, which shows that both servers are virtualized on VMware hypervisors. We can now see everything that is happening by viewing the infrastructure diagram. As shown, there is a lot more software running on these servers, as well as many more dependencies and connections, and even Java applications deployed on WebLogic that do not define the business logic of this application. We can go back and take a look at the default architecture diagram and compare that to what all we have available for us to view. Here we see that the imaging Java application is deployed on the Oracle WebLogic server. We will refer back to this information once we get to the edit page. We have taken a look at all of this information and know that it is no longer an unknown application. Our next step is to edit this information by giving it a name. We will call it imaging, based on the information we identified in the application diagram. The environment will be labeled production. If we save and return to the home screen, we will notice that the business applications object has been updated from 25 applications to 26 applications. Our newly created object is listed at the bottom of the page. We can repeat this process for the remaining unknown applications, one by one, sometimes splitting those intertwined applications into multiple applications, sometimes merging them.
By mapping every server to the related business function at modelizeIT, clients are also able to identify unused servers that may be candidates for decommissioning. We found that clients often discover that 10 to 20% of their servers are unused. The process of grouping business applications into affinities is jump-started by modelizeIT's affinity grouping algorithms. The first thing to point out is that multiple applications can be hosted on a single server. In the context of grouping applications into affinity groups, this means that we need to be able to go lower than just the server level and understand the communication that occurs at the software level or even the individual software instance level. In this image, we can see that ABC app on server 4 is interacting with the ABC data database on server 3, both colored violet. At the server-to-server communication level, we wouldn't know any better than to just assume that server 4 and server 3 form an affinity group. But by knowing that ABC app actually only interacts with the ABC data and not the entire SQL server, we can conclude that ABC data can be migrated separately from the rest of server 3 as part of ABC app's affinity group. Affinity grouping is based on application relationships that cannot be interrupted. modelizeIT automatically detects those dependencies and groups the applications into the same affinity, highlighted here in green. It knows which dependencies can be interrupted based on an array of application models. This helps ensure that critical functionality remains intact throughout the migration. Another important challenge is understanding network flow through load balancers. Once traffic enters a load balancer, it becomes difficult to tell which application is actually serving the request. modelizeIT accounts for this by ingesting and analyzing load balancer configuration dumps, allowing it to determine which backend systems actually receive traffic. It then traces those flows downstream, giving planners a more accurate view of dependencies and affinity groups. Now we'll present an affinity grouping demo.
In this video, we will group business applications into affinity groups based on their critical dependencies. I am clicking the Unknown Affinities tile and clicking the Identify button. You can see many affinity groups created by the tool automatically. Each affinity group can be migrated independently. So many small affinity groups means flexibility in terms of assigning them into migration waves. This is good for the migration planning. Let's look at affinity group 269. You can see in this case, the affinity group consists of two business applications that have a critical dependency. They both use an Oracle database. In corporate IT environments, all servers are interconnected via dependencies on DNS, Active Directory, various monitoring, backup, and other systems. As you can see, these two applications do depend on so many other applications, but the tool knows that these other dependencies should be okay to interrupt during a migration. Without this automation, you would have to make such decisions manually for each dependency, potentially millions of them. Let us save this affinity as Primavera Affinity Group. Of course, this is a simple affinity group. In more complex situations, you will need to add or remove contents of affinity groups by working with the application owners. However, even for these complex cases, the tool eliminates significant portions of otherwise manual work.
Finally, stage 3 of the migration pipeline involves assigning each affinity to a wave. modelizeIT is able to work around a multitude of constraints to build an optimal migration plan. The process is highly customizable, allowing migration consultants and clients to build their own migration rules, set their own timelines, and shape migration waves around real business priorities and dependencies. In the images on screen, we can see that we restrict the total amount of storage per wave to just 1 terabyte, limit the complexity, which is a user-defined metric, to 70, and require that each wave contain at least one piece of telnet software. modelizeIT can model technical constraints, such as particular software versions, as well as arbitrary user-defined business constraints, such as criticality or complexity. We can also model deadline-based constraints, so a team can force outdated systems to be migrated by a fixed date, or require applications tied to expiring software licenses to move early enough to avoid renewal costs, compliance risk, or operational disruption. We'll show you a live demo of the first few features now. Let's go over how to create migration waves using the modelizeIT tool. As we see, we already have 22 affinity groups created. Now let's head on over to Move Waves. As we see, we don't yet have any waves created, so let's hit identify. Here, we're going to set wave start date to January 3rd, 2027. That's when we expect the first wave to occur. Here, in the phases template, we're going to choose how every wave is going to look. So currently, we just have one phase, the migration phase. Let's make it a little more granular. First, let's add a cutover phase. We're going to name it cutover. And let's change the color to be a little bit darker, just to indicate that we should give more attention to this phase. And we'll make it 1 day. In addition, let's also add a hypercare phase. And let's make it 3 days. And also, let's add a plan phase. Now, let's just hit identify and see what it creates. So as we see, this isn't very interesting. It basically just put all the affinities in one wave, right? So let's fix that. Let's hit identify again. This time, let's add a constraint. We're going to set n-affs, which is just the number of affinities, to be less than 4. N-affs is based on a rule that was already created. We'll show you later how you can create your own rule. So let's hit identify again. Now, we can see that multiple waves were created, and each one follows this rule. But now let's suppose you have a blackout date. That is a date where you can't actually have a migration going on at that time. So let's actually hit add. And let's call it blackout. We're going to make it a week long. And let's also call this blackout. Let's move it to, let's say, February 14th. So this is saying that the week of February 14th, we can't have any migrations going on. Now, when we head back to move waves, we'll see it's present, but currently there's still a wave at that time. We'll actually have to hit identify again. And as we can see, the rule was followed. All of the waves were created around that blackout date. Let's now go over how to create our own rules. So we're going to head on over to Rules and hit Add. And we're going to call this one Complexity. So complexity is going to depend upon the number of nodes and the number of instances. So we'll do +5 for every node, and we'll see that we're going to duplicate this, and we're going to go to hit add again. We're going to do this for instances as well. We're going to do +1 for every instance. In addition, let's create another rule that accumulates the total amount of storage that the nodes are going to be migrating. So let's call it total storage. And it's going to be in gigabytes. So in the value field, we're going to put plus @cp fs gb. And in the condition, we're going to put @cp @node. So now when we go back to move waves, we're going to hit identify again. And this time we're going to edit the constraints. So let's remove the existing one. Let's add a new one. This one is going to do, it's going to limit the complexity, let's say to 150. We're also going to limit the total amount of storage per wave. We're going to do, let's say, 1 terabyte. And in addition, we're going to add one more constraint. So we can actually edit the deadline or a minimum date for specific objects, right? So in this case, we have some Windows 2003 nodes, and we want to prioritize those. So we're going to set a deadline for those. Let's type in @node OS description. And we're going to put in a little regex here, .star Windows .star 2003 .star. And we're going to ensure that this comes, let's say, before maybe February 1st. And let's hit identify. So as we see, we are still following the blackout date from earlier, and we're limiting the total amount of storage transferred per wave to 1 terabyte, and the complexity of each is around 150 or less. And within the contains, we'll see that all Windows 2003 machines, here we have Windows 2003, are before that February 1st cutoff. modelizeIT wave planning can also arrange application environment dependencies where, for example, production applications should only be migrated after their development and test counterparts. That allows teams to validate the migration approach in lower risk environments first, uncover issues earlier, and bring proven changes into production with greater confidence and less risk of disruption. We'll now show you a demo of implementing migration wave dependencies. Suppose that our constraints list only restricts the total complexity per wave. In this case, the limit is 140. We might run into a bit of an issue. When we inspect what is contained within each migration wave, we'll see that a lot of production affinities are being migrated before their dev counterparts. So here we see that this affinity, the production version, is being migrated before the dev version right here. Let's hit identify again. The modelizeIT wave planning tool can help model this dependency. In the environment dependencies field, we can input dev, prod. This time, when we open the contains lists, we'll see that for every single prod affinity, the dev affinity will have been migrated first. In order for this to work, the applications and affinities have to follow a certain format. Let's go to Business Apps, MIT AJ app as an example. We'll see that this application actually contains both of the dev and the prod version. So let's hit the prod version. And the prod version is contained by both the affinity and the application. Don't worry though, this format will automatically be created when you import the applications. To make things clearer, here's a diagram of the relationships between affinities and applications from different environments. On the left side, we see that the dev version of app1, which has a dashed border, is contained by both the dev affinity and also the parent application. Likewise, the prod version of the app, which has a dotted border, is contained by both the prod affinity and the same parent application as the dev app. This allows the system to recognize that the affinity containing app1 prod should come strictly after the affinity containing app1 dev. And again, when you import application mappings through the UI, this format will automatically be created for you. Now, let's go over some of the types of reports modelizeIT can generate. modelizeIT identifies thousands of products, so you can do aggregate software analyses like downloading a report of all IBM DB2 installations. Oracle and Microsoft licensing analysis is typically critical for proper business case development for large enterprises. modelizeIT is used by Oracle Platinum level partners to defend Oracle clients against Oracle audits. This means the tool can do high quality Oracle licensing assessments, not just some high level estimates for migrations. modelizeIT can analyze more than 180 Oracle products and more than 150 Microsoft products. For Oracle, you get two reports. First, a summary report, where you can see which Oracle products, features, and packs are used, how many CPUs in the underlying CPU pools need licensing in the current environment, and how many licenses you'll need for the same instances in AWS. Second, you get a detailed report with individual products and details, like when each product was last used and how many times it was used. All this is done for various CPU and virtualization configurations. Oracle licensing can vary dramatically depending on how virtualization layers are configured, and the tool can account for that across Windows, Linux, Unix, and the related virtualization technologies. Microsoft licensing analysis is dramatically easier than Oracle. modelizeIT analyzes Microsoft products with summary reports for SQL Server and Windows. modelizeIT provides its own strategy and capacity planning recommendations. They are based on the provisioned as well as utilized capacity, referred to as max and min in the tool respectively. The tool takes licensing costs into account when suggesting AWS instances. So for instances with per core licenses, the tool can suggest more expensive instances if it results in lower overall cost. Likewise, it can also suggest turning off some CPUs to save on per core licensing costs. modelizeIT can also facilitate modernization projects by suggesting instance sizes for architecture changing migration, like when CPU and virtualization architectures change. An example would be a migration from AIX LPAR on Power CPU with a shared uncapped CPU pool to an AWS Linux instance with a fixed CPU size. An uncapped shared CPU pool is shared by multiple AIX LPARs, and this virtualization construct cannot be identically represented on Intel CPUs. When performing this type of sizing recommendation, the system uses CPU benchmarks, its knowledge about virtualization technologies, observed utilization metrics, and information about the workloads. As an added bonus, it can trick the AWS MPA tool to use these recommendations. There are also other metrics that you typically do not see available to you. For example, the tool captures the amount of cold cache used, so even if you see a server with all of its memory used, you can still provision a smaller amount if the system just uses some of that memory to keep files cached that are not accessed anymore. You can often be more aggressive with the capacity planning in that case. The capacity plan view also presents metrics about the number of all, the number of non-infrastructure, and the number of critical dependencies. These metrics help estimate the complexity of migration for each server. The modelizeIT system also collects resource utilization information. Each utilization metric is captured in the form of a timeline. In addition to the standard metrics like CPU, memory, and swap utilization, the system also captures I/O rates and data volume metrics for disks, file systems, and network interfaces. In this callout, you can see latency metrics for NFS read requests. NFS-related metrics are collected for each mount point individually, so that you can plan storage-related modernization scenarios by looking at the storage used by the clients. There are lots of existing tools for modernizing specific software stacks to other specific software stacks. However, in order to assess the possible migration scope and actually use these tools, you first need to discover the current software stacks and their installation configuration details. Then, only after assessing if modernization is possible and desirable can you apply these tools. A classic example is the replacement of IIS-based .NET applications with Linux-based deployments. In the diagram on screen, we see that we have a large list of initial servers. modelizeIT can identify the servers using the target migration pattern, like the IIS-based .NET applications mentioned earlier. Then, we can conclude that only a fraction of these are desirable to migrate. In this example, that's just 4 servers. Security zone planning is part of any cloud migration. modelizeIT can be used to plan security zones and create reports with estimates about what connections will cross security zone boundaries. This is used by clients to create initial firewall rules. Now, let's discuss the supported platforms. Here's a list of server operating systems supported by modelizeIT. Essentially, we strive to support operating systems released in this century. And it's not just operating systems. For example, we also support Microsoft SQL Server 2000. It is true that 20-year-old operating systems such as Windows 2000 and Windows 2003 are not common anymore, but many clients do still use them. We do projects all the time where some other assessment tool was already tried and deployment failed because of some kind of tool inflexibility. So, we know from first-hand experience that while this may look like a small deployment limitation at the beginning, it can actually stall data collection projects later down the line. modelizeIT supports all popular virtualization systems on Windows, Linux, and Unix operating systems. In this image, we see an example of a Sun, now Oracle, physical server running 3 LDOMs, which are Solaris virtual machines, and a Solaris zone, which is a container within an LDOM. Virtualization dependencies are shown with dashed lines. Here, modelizeIT goes below the host level and identifies the individual Docker containers and the software running inside them. Instead of treating the server as a single unit, it shows which application components are containerized and how they should be understood in the migration plan. modelizeIT supports pod and service level architecture discovery for Kubernetes and OpenShift clusters. In this diagram, we see services, pods, and the software corresponding to each of the containers of those pods. When modelizeIT analyzes business application architecture, it analyzes various clusters. Modeling OS-level clustering on Windows, Linux, and Unix operating systems is easy. However, modelizeIT also analyzes middleware-level clustering. For example, here you see an Oracle WebLogic deployment on 4 servers, where 3 domains are used to host Java modules, and one of these domains only spans 3 nodes. Rather than stopping at server-to-server relationships, modelizeIT identifies the actual middleware cluster structure inside the environment. In this case, it understands which WebLogic domains span which nodes, which modules belong to each domain, and where cluster boundaries really are. modelizeIT supports discovery of cloud-native resources, including those on AWS, Azure, GCP, and OCI. It focuses its analysis on the architecture of the business applications rather than simple inventory. In this diagram, we see an AWS Elastic Load Balancer forwarding requests to an Oracle WebLogic server running a Metarec application that uses the RDS Cloud-Native Oracle database. Thus, in-server details are combined with cloud-native architecture details. Many enterprise clients have mainframes. Even if mainframe migrations themselves are out of scope for a project, mainframes may have interdependencies with various other servers. In this screenshot, you see a Windows-based IIS application pool connecting to a DB2 database on a mainframe. modelizeIT can either discover mainframe details, or related information can be imported as a CSV template filled in by a mainframe administrator. Now, we'll discuss modelizeIT integrations with AWS. AWS offers an internal and SI partner-focused program called the DAP Assessment. At the very highest level, it's a program that offers a no-cost deployment of resources, a process framework, and the technical tooling needed to not only catalyze and accelerate migrations, but also increase the likelihood of successful outcomes. It offers a unique competitive advantage that increases velocity, win rate, and, ultimately, lifetime value. So, how do modelizeIT and the DAP assessment fit into the AWS migration framework? The DAP assessment takes place during the assess/identification phase and extends into the mobilize phase, accomplishing 2 key goals, each of which is accompanied by a package of migration planning deliverables. The first goal is helping clients build the business case for change. This is achieved by first performing a comprehensive infrastructure and application discovery that serves as the foundation for the TCO report and a license optimization assessment. The second goal, and this is the key difference from a standard assessment, is helping clients prepare for and accelerate their mobilize engagement. It includes application discovery and dependency mapping, as well as the delivery of the initial migration strategy and initial migration wave, essentially teaching them how to migrate to AWS. To be clear, this is not a full wave migration plan. Rather, it's an early stage engagement that provides the data points needed to move into and accelerate their mobilize engagement. Once a customer moves into mobilize, they have the option to extend their AWS-funded modelizeIT license and execute their full migration roadmap, whether it's customer-led, partner-led, or ProServe-led. Here's a quick overview of the DAP engagement process. I'm not going to get into detail here, but you can see that overall, the DAP assessment takes about 6 weeks to complete and is a partnership primarily between the customer and a service delivery team. modelizeIT also offers an easy integration with the AWS MPA tool. You can download an Excel export file and upload it to MPA with a few mouse clicks. So, for simple business case development situations with AWS, you can rely on the MPA tool. The AWS Transform team also has the capability to consume modelizeIT reports. Finally, let's discuss deployment. We'll go over how to facilitate both the data collection and data analysis. This diagram shows the overall deployment architecture of the platform. On the left is data collection, and on the right is analysis, and that separation is intentionally there. It's there for privacy, security, and deployment flexibility. Once data is collected, it can be sent either to a modelizeIT managed SaaS analysis server or to a Linux-based analysis server deployed inside the client's own environment. The SaaS option reduces administration, while the on-prem option keeps all collected data under the client's control. The other important point on the slide is that collection is not limited to a single mechanism. Data can come from the gatherer, from existing third-party tools such as SCCM or Ansible, or from additional existing sources the client already has. That includes cloud sources, VMware exports, load balancer configuration dumps such as F5 configs, CMDB application definitions, and even manually maintained inventories such as CSV files. The idea is to combine these inputs so the platform can build a much more complete picture of the environment without forcing everything through one collection path. Another important design point is that all collected server data is stored in plaintext.out output files, so the process is fully auditable. Regardless of the deployment method, clients can review every bit of data, including how and what information was collected. The image shows the first few lines of an example .out file. We can see that both the commands and their outputs are visible. The key point in this matrix is that collection and analysis are independent choices. You can use the gatherer, you can use existing third-party IT tools, or you can combine both, and any of those collection approaches can feed either the SaaS or the on-prem analysis options. So, the client is not locked into a single deployment model. They can choose the combination that best matches their tooling, their operation model, and their privacy requirements. In fact, if you choose to go with already deployed third-party tools and the SaaS analysis server, you can deploy modelizeIT without installing a single additional server or appliance. Let's dive deeper into the differences between the SaaS and the on-prem analysis server options. With the SaaS option, modelizeIT manages the analysis environment for you. That makes the platform easier to stand up because the client does not have to provision a server, deploy the software, or handle the data processing administration. The trade-off is simply that analysis is managed outside the client environment, which is why some organizations prefer SaaS for convenience and others prefer on-prem for maximum control. With the on-prem option, the client builds a Linux-based analysis server in their own environment, and all collected data stays there. That gives the client full control over privacy and access, because nothing leaves the environment unless they explicitly decide to share it with the teams working with them. The trade-off is that the client takes on the server build-out and software administration themselves. The on-prem analysis server option also supports single sign-on and can therefore integrate with systems like PingFed. Now, let's look at how either the gatherer, third-party tools, or both perform data collection. The gatherer, a Windows-based component, is the classic collection approach. The team inputs credentials and a list of target servers, and the tool uses them to log into those systems and collect data into text-based .out files. Under the hood, this is not a traditional installed agent. The gatherer starts an in-memory sensor process. That process writes to a local text file, and when collection is done, it exits, leaving behind only the output file. The first thing the gatherer does after beginning the data collection is set itself to run at low priority to avoid interfering with production workloads. For deep configuration details, you typically do need elevated access, such as sudo on Linux and Unix, or local administrator on Windows. For Windows, the discovery targets will need to have port 445 open. If the Windows targets are really old, they might also need to open port 139. For Linux and Unix discovery, the targets will need to have their SSH ports open. Also, for environments that use CyberArk, the gatherer can integrate with it directly for credential retrieval. That allows clients to follow existing privileged access workflows without manually managing credentials throughout the collection process. If the client already has tools such as SCCM, Ansible, or other similar operational platforms, modelizeIT can work through those instead of relying only on the gatherer. This is especially efficient for clients that have already invested time and effort deploying third-party tools across their environments. In that case, we provide lightweight sensors for those orchestration tools to run. The output is written into the same auditable .out files that get transferred to the analysis server for analysis. That means the client, again, can review exactly what was executed and what data was collected. It should be emphasized that with this deployment option, there's no need to create any user accounts or firewall exceptions. This means that clients can reuse the efforts they already spent deploying these tools. A nice example of this is a pharmaceutical customer we had in the past, which managed to collect data from tens of thousands of servers within just 2 weeks. Documentation is available for collecting data from load balancers, RV tools, Cloudflare logs, and job schedulers. The general process for these is you either upload configuration dumps or run our platform-specific discovery. Now we'll provide a demo of the gatherer. I'm going to show you how to perform the data collection process using the modelizeIT gatherer software. We're going to copy and paste the servers we'd like to perform data collection on. We can either input domain names or just the IPs directly. We should also separate out the domains based on the OS and credentials. First, I'm going to create WinTargets1, containing a list of some Windows machines. Then, I'm going to create LinuxTargets1, containing a list of some Linux machines. I'm also going to create LinuxTargets2, which contains a different set of Linux machines that use a different set of credentials. Finally, I'll create a target called SunTargets1, which contains a list of SunOS targets. Now, let's create the credentials for each of these servers in the parameters section. We're going to create WinParams1, LinuxParams1, LinuxParams2, and SunParams1. This is going to be of type Windows, and we're going to use the username and password. Now let's create LinuxParams1. This is going to be of type SSH. Again, using the username and password. Now we're going to make LinuxParams2, also SSH. However, here we'll use a different port. We'll use 130. Finally, let's create SunParams1. Again, using SSH and the password. Here, we're just using username and password, but other authentication methods are also available and can be found in the documentation. Now, let's actually create the data collection jobs. First, we'll run some test connectivity jobs. This will ensure that our credentials are formulated properly and that we are able to form a connection between the gatherer and the target servers. We'll use the WinTargets1 and WinParams1 using the test connectivity windows. For the SunOS and Linux machines, we'll use test connectivity Linux/Unix. And we'll schedule them all for now. And I'll refresh a few times here to see when they finish. We see that each of these has succeeded, indicating that we can move on to the application data gathering jobs. Just like before, we'll use the same set of credentials. And again, let's schedule them all for now. Now that these jobs have been created, we can expect to see their statuses transition from scheduled to starting to verifying. Once the state is in starting, the data collection on the remote server has successfully begun. Then, after being in the starting stage for 2 minutes, the gatherer will begin the verifying stage. Let's come back in 2 minutes. At this point, the gatherer will fetch what has been collected within those 2 minutes on the remote servers, inspect their contents, and ensure that everything is running smoothly. Finally, it will move on to the started stage. This is the main data collection stage, and it will continue to run in this stage for 1 week. Let's come back in a second. Right now, if we go to Files, we can see what has been fetched from the initial scan. We can see that each server has its own file. Once the data collection process is finished, these files will be updated to reflect the connections, utilization metrics, and software configurations that have been automatically acquired. The software periodically sends 68-byte packets to the modelizeIT update and licensing server. They contain only the information necessary to validate the license usage and check for updates. modelizeIT can be deployed in air-gapped environments for highly sensitive clients. This is less convenient and requires manual updates and license validation from the client side. However, it does satisfy the needs of our most sensitive clients. This was Alexander from the modelizeIT team, and I thank you for watching.